Okay, we're going to be doing example 5. I'm doing one video per example just to try and piece it out for you guys here. So let's go ahead and follow the same patterns that we were looking at before, looking at our bounded regions, determining which our axis is rotation, where we're rotating around, and then also take a look at those helpful questions, whether or not we're attached to the axis of rotation, and also which direction we're traveling in. So first, this is just a linear equation. It's x plus 1. That means that I'm going to have a linear equation, diagonal line, x plus 1. I'm going to go out to the line, or the value x equals 3. So it's going to look about like that. So I'm going to come down here to 3, and out here to 4 on the y-axis. So this is the area that we're looking at. So when I travel on the x-axis, I'm going from 0 to 3. On the y-axis, it's going to be from 0 to 4. So as we're going around the x-axis, we're rotating around the x-axis. The question that we first ask ourselves, are we attached? Yes, we are. So we just need the big R squared. We don't need the little r at all. So my volume is going to equal pi times big R squared. Now I need to figure out what's my direction. And I'm traveling left to right since I'm spinning the opposite direction. So it's going to be dx. And then my boundaries are in terms of x as well. So x is from 0 to 3. So let's figure out what that big radius is. It's actually pretty straightforward. It's just from that top edge down to the bottom, which in this case is just the function x plus 1 and then minus 0, or just x plus 1. So this is almost too easy. So we have the volume equals pi times the integral from 0 to 3 of x plus 1 quantity squared dx. Let's see how it gets a little bit harder as we change things. Now when we're going around the y-axis, we're actually going to need to look at this a little more carefully. We still have that same equation, y equals x plus 1. We're still going out to about 3 here, which means that we hit 4 on the x-axis. Let's make these in gray just to make it a little bit more distinct what we're actually drawing here. So again, we have this blue shaded area. And notice that we got empty space, but only for part of it. So when we ask the question, are we attached? Some of the time, yes, but not all of the time. We're attached from here to here, from 0 to 1, but from 1 to 4, we're not attached. So we're rotating around this y-axis. So I'm going to have two separate integrals. I'm going to go from 0 to 1 on the y-axis, which means in the direction of y. Then I'm also going to go from 1 to 4 in the direction of y with pi here. So from 0 to 1 I'm attached, so I just need to figure out what that big R is. But from 1 to 4 I have a difference. I got to subtract that inside difference and figure out what the leftover is going to be. So now that we're going in the direction of y, our radius is going to be horizontal. So this first R, the first big R, is just from, what's this, x equals 3 to 0. So that's 3 minus 0. For the second one though, actually for the second one it still remains the same. R equals 3 minus 0. But the little r on the inside makes this change a little bit. Now we got to subtract this little r, and that's going to be that outer edge, which normally is y equals x plus 1 in terms of x, but we have to change that to terms of y, so it's y minus 1 equals x. So r equals y minus 1, we can say minus 0 to get back to the axis of rotation. So this is really the big R equals 3 both times, and the little r equals just y minus 1. So when we're going from 1 to 4, it's y minus 1. But when we're going from 0 to 1, the little r is just 0. There's no radius on the inside. Similarly, from 0 to 1, the big radius is 3, but also from 1 to 4, it's still 3. So we have to split this up into two integration expressions here. Volume equals pi times the integral from 0 to 1 of just 3 squared dy. Plus, the second one's from 1 to 4, we still have the pi, but now we have big R squared minus little r squared. It's going to be 3 squared minus, and then y minus 1. Now some people actually might do some different type of combining here. They notice that the r squared is the same in both. You could have written this as the integral from 0 to 4 of big R squared minus the integral from 1 to 4 of little r squared. Both ways would have worked. Either way is fine. Okay, let's take a look at the last part to example 5. There's only a, b, and c for example 5 and 6 here. We're rotating around the line x equals 3. Let's go ahead and get our visual reference. We got our x-axis and y-axis. We have our linear equation. I'll draw that in gray. It's going to be x plus 1. And then we come down to x equals 3, go up to y equals 4. We still have this blue area. That part hasn't changed. Now again, we're going to have a little bit of change here in the idea that we need two integrals, because we hit a breaking point here where our radius is variable. It changes in that top 2/3 or 3/4 of that. But in the bottom part, it doesn't change. Down here, it's just constant. So from 0 to 1, it's not going to change, but from 1 to 4, it does. Thankfully, it's actually attached the entire time, so I really just have to go from pi r squared. I have to go from 0 to 1, figure out what the big R is, but then see how that changes from 1 to 4. We still have dy because we're going in the y direction. We're traveling this way because we rotate around the line x equals 3. Then that means that my big R to start with is going to be from 0 to 1. It's this whole length here between these two lines, and that's pretty easy to find because it just goes from 0 to 3. So that's just 3. For the second piece though, the radius starts at 3, but then it goes down to this slanted line. So it's going to be 3 minus, and then that function in terms of y, which is y minus 1. Now if I were to simplify that, that would be 4 minus y. So this line right here, this radius, is 4 minus y. So let's go ahead and write out what the volume would be. It'd be pi times the integral from 0 to 1 of this r squared, which is 3 squared, dy, plus, now we have the second half from 1 to 4, still with the constant pi on the outside. And then big R is going to be 4 minus y quantity squared, dy. And there we go. Next we'll have example 6.